Hello and welcome to the second video in a series of video modules on using Qnect for connection design. In this video, we're going to take a quick break from connections and talk briefly about the layout of the integrated design project building being used in this project. This building is a 4-story office building with 1 story below grade, meaning that there is a basement. It's located in Downers Grove, Illinois, which is in a low seismic region. It is a 102,000 square foot building. The story heights in this building are 13'6", which is somewhat typical floor-to-floor heights in office buildings. Bays are defined as the spaces between the columns. In this building, the bay sizes or spacing between the columns is relatively uniform. If we look at this in plan, we'll be able to see this more clearly. Now, I do want to mention as we're looking at this in plan that what you're seeing is multiple floor levels all on top of each other. So we're seeing all of the floors in this just one floor plan. So you're seeing gray framing, this is roof framing, and the green framing is the floor framing at floors below. So it does look a bit unusual with what looks like very closely spaced beams. This is just because we've superimposed all of the floors on top of each other. Now, that is not the point of why we're looking at the floor plan, though. We want to look at the floor plan to be able to look at the column locations. And what you'll see is that columns are typically tied to these grids. So we have grids 1 through 8 indicate column locations, and then grids A through F. The spacing between the grids are uniform in the east-west or left-right direction. And these bays are 30 feet long. So from 1 to 2, that's a 30-foot span. From 2 to 3, another 30-foot span. In the north-south direction, we have columns located at A, C, D, and F. So we have bay spacing from A to C is 45 feet, from C to D is 30 feet, and from D to F is 45 feet. Uniform bay sizes allow for the same member sizes and connection details to be used repeatedly. This leads to a more cost-effective design. Orthogonal layouts, meaning that the beams frame into girders or columns at right angles and not skews, also means more efficient and simplified design and detailing. So for example, if we look at this gray framing coming into this purple framing, you can see that they meet at a 90-degree angle. There isn't some kind of other skew, other angle besides 90-degree angles. Orthogonal framing means you're framing things in at 90-degree angles. It may not always be possible to lay your system in a uniform and orthogonal way, but efforts should be made early on when coordinating with the architect to try to achieve this whenever possible. The Tekla model only shows steel framing and connections and does not show concrete walls or slabs. The beams at the ground level, shown down the lowest level of beams here, actually frame into a concrete foundation wall that wasn't drawn for the purposes of needing to do any kind of steel connection design with Tekla. These beams can be connected to the concrete using a variety of anchor types, and you can see that this connection here has an end bed plate attached to the beam, and then these stud anchors are used to connect to the concrete walls. The green beams that you see throughout and the lighter purple color represent gravity framing within the building. Gravity framing is designed to withstand gravity loads, such as dead loads, live loads, and snow. The connections in gravity framing are typically simple or pinned connections without much rotational stiffness. In the United States, we typically use wide flange shapes as our beams and columns, and so you can see that these I shapes are used for beams as well as columns. At the roof, you'll see steel joists shown in gray. These are open web, lightweight steel trusses. They are typically able to span long distances and allow for utilities such as plumbing, conduit, and occasionally small ductwork to run through the members. However, joists may experience more vibration issues than traditional hot-rolled shapes like wide flanges. Roof loads are usually less than the floor loads, and vibrations are not typically an issue at the roof, so using joists as roof framing is somewhat typical. You could, however, also use these joists to support floor levels, or you could choose to use rolled shapes at the roof instead of joists. These are all considerations for the structural engineer to make. The beams, joists, and columns in the gravity system make up most of the framing for the structure. You can see that the gray joists, the green beams, and the light purple columns represent most of the framing of this structure. But this gravity framing is not designed to withstand the lateral or horizontal forces. Instead, lateral systems are designed in strategic locations in the building to withstand lateral loads, such as earthquake and wind. These loads try to push the building over, and the lateral system is a specialized system to withstand these forces. There are a variety of lateral force resisting systems that can be used, including braced frames, moment frames, and shear walls. These systems are typically much more expensive than gravity pinned connections and framing, and so optimizing the lateral system and using it in appropriate locations is very important. The purple framing, these 3 bays on either side of the building, so you can see the 3 bays here, 1, 2, 3, and then on the opposite side we also have 3 more bays that look similar, 1, 2, 3. These represent moment resisting frames. These moment frames are designed with fixed beam to column connections to prevent the frame from being pushed over due to wind or seismic. There are a total of 6 bays, again 3 on either side, that act to resist lateral loads in the east-west or left-right direction. The yellow framing on either side of the north-south direction, so the frame that's here and the framing that's on the other side, these are braced frames, part of a braced frame lateral system. You can see that we have vertical braces here that are used in an upside down V, also known as chevron configuration. These braces can be oriented in a number of different patterns, and they help to resist lateral forces as well. A total of 2 bays of the brace frames is used, one on either side, this side and then the other side. But brace frames are typically much more stiff than moment frames, which is why only 2 bays are needed versus the 6 bays needed for the moment frames for this structure. Brace frames, however, have more architectural restrictions than moment frames. You can see if we look back at the moment frames, you can see that moment frames still allow for open bays. There's space below the beams and between the columns, but the braced frames have these vertical braces that could inhibit architectural flow. Braces are commonly placed on the exterior of the building or hidden within walls in locations that have been closely coordinated with the architect. If we take a moment to think critically about where these lateral frames are located, what do you notice? Let's go ahead and look at it in plan view. The frames are located in both the north-south and east-west direction. Wind and seismic can come from both directions, so we need to ensure that we have been considering loading from all directions in our design. This includes a combination of loads in both directions. So when we're applying a load in the east-west direction, we're going to engage the purple moment frames. When we're applying load in the north-south direction, that engages the yellow braced frames. And we also consider a combination of loading in both directions to represent more of an inclined load that's not exactly orthogonal to the building. The lateral framing is also symmetric. There's the number of frames that's used on either side of the building is the same, 3 and 3 and 1 and 1. This prevents torsion or twisting of the building, which would occur if one side of the building was much stiffer than the other. The lateral framing is also located around the exterior walls. Lateral frames can occur at the interior bays of the structure, but engineers often like to locate them at the exterior walls if possible. The further apart your lateral frames are, the more resistance you have to torsion and the less torsional load you'd see in each frame. So if we were to look at our floor plan and we're seeing some type of effect due to torsion, some kind of twisting of our frame,
This would be related to this torsional moment. And how we resist that is by having these torsional shears in our frames. The further apart that we space these, the less force that they need to have because there's a larger moment arm to resist that torsional load.
Also, by putting braces and deep moment frame members on the exterior, there are less issues negatively impacting the architectural layout of the spaces. Finally, the model doesn't show the floor slab, but we typically use a concrete slab on metal deck for steel-framed buildings. This floor slab provides a surface for people to walk on and for the gravity loads to transfer. But the floor is also a way to transfer lateral forces to the lateral system. If you think of wind hitting the side of this building, the wind will hit the exterior walls, transfer to the floor to each floor level above and below, and then transfer through the floor until it gets to the moment frame structure and ultimately down to the foundation. So if we zoom in and just look at what would happen at one floor, we have this, I'm showing a uniform area load to represent wind being applied to your building. Part of that load will go up once it hits the whatever the exterior is, curtain wall or metal panel exterior wall. It's going to go up to the floor above and down to the floor below. Once it gets into the floor, it needs to find its way to the lateral system, to the moment frames in this case. When the floor functions in this way to resist lateral loads and transfer lateral forces, it's called a diaphragm. The floor slab must be designed to ensure that it can transfer loads to the lateral system without failing in shear or flexure or deflecting too much. If your lateral frames are placed too far apart, you may have issues when designing your diaphragm as it needs to span too far of a distance. So you need to take the diaphragm into consideration when you initially lay out your lateral framing. This building shows you just some of the many design considerations that you as the structural engineer will need to make in order to design a safe and functional building structure.